Hello and welcome back to Ganesh Institute channel. So in today's video we are going to discuss how to find out the JC form or Jordan Canonical Form or Jordan Normal Form out of a matrix. Okay, so let's see what terminologies are there in order to understand this concept. Okay, so first thing is, what is Jordan matrix or a Jordan block? Okay, so first of all, you have to have a matrix which should be a square matrix, that means m by m order. Let's say this matrix is of 3 by 3 order, okay, for an example. Now, in order to be a Jordan matrix form, what should we have is all the elements, let's say 4, all the elements in the diagonals must be same. Below the diagonal, you should have all the elements as 0. above that above that diagonal, you have to have 1 as your element, and above that 1 you must have 0. Then you can say that this square matrix is of Jordan block type. Okay, now if you see, let's say this is of 4, all the elements which are given here in terms of diagonal are 4. If you have, let's say anything, let's say 2 by 2 order of matrix, you have 2 0 0 5, and if it will be asked that this is your Jordan canonical form. Now let me tell you what's the difference between Jordan block and Jordan canonical. So in Jordan block, your diagonal elements must be same, but in Jordan canonical form, diagonals need not to be same. Okay, and thereafter all the elements other than those diagonal matrix, if you see here, what are they? 0, correct? So if you have to find out from the Jordan canonical form what would be the Jordan block, then you will see here you can come up with 2 Jordan blocks. You know very well that this is something, if you see, other than diagonal elements, all elements are 0, right? So these two would be the eigenvalues of this matrix, correct? So 2 and 5 would be the Jordan blocks for this Jordan canonical form. How we have found this out? So let's see with an example. So whenever you have a matrix of 2 by 2 order, then always you can find out from it Jordan blocks which must be less than that order or equivalent to it. So this is of 1 by 1 order, this is of 1 by 1 order. Obviously, this is less than the order of the parent matrix, correct? Let me give you another example. You have this 5 0 0, 1 5 0, and 0 0 minus 9, right? Now, in order to be a Jordan block, what we require is all the diagonal elements must be same, above that 1, and rest all elements 0, right? So you can see these two diagonal elements are same, above that it is 1 and below that 0. So this can be one Jordan block. So 5 0 1 5, this can be one Jordan block which can be brought up from it. And apart from that, you can have this as a Jordan block. Why? Because if you see, we can only make Jordan blocks from the diagonal elements, right? So 5 5 minus 9. Now minus 9 is the separate entity which we can come up with. So this is of 2 by 2 order, this is of 1 by 1 order. Remember, when you do the sum of the orders, it must be equal to the order of the parent matrix. Okay, so here if you see, what is given to us is a question to convert Jordan canonical form from a matrix. Now here you have to convert into Jordan canonical form. This matrix is given to you. So in order to convert Jordan into Jordan canonical form, you have to remember few steps, okay? Let me give you, it will be more of question like, and you will get the concepts from the question, okay? So this is your matrix. Now just like we do in order to find out any eigenvalue, we have to firstly find out characteristic equation, right? So we will do same here also. So characteristic equation, and that is what? Determinant of A minus lambda I should be 0, right? What would be A minus lambda I? So if you see, lambda I is the identity matrix where diagonals are 1. So you have to multiply that 1 with lambda. So lambda and all rest elements would be 0. Correct? So if you subtract lambda I from A, what will be that which you get? 5 minus lambda, here 4 and 2 as it is, then 4, then 5 minus lambda, then 2, then 2, 2, and then 2 minus lambda. Correct? Now you have to substitute it as 0 and find out the value of lambda. That means the eigenvalues. So the easiest trick, if you want to find out, because this is the very long process, one trick which you can come up with is this. So because it is of 3 by 3 order, so you will definitely get, you are going to get lambda cube anyhow, right? Minus, the formula would be, you have to take the summation of the matrix where you have diagonal. Your diagonal matrix is what? 5, 5 and 2. So 5, 5 and 2 lambda square. So you are decreasing the order, lambda cube, then lambda square. And then if you take, we are just expanding it. You can do your conventional method also. That is also fine. We just need the right answer, correct? Now, here what you need to take, you have to take the minors. So firstly, if you hide first row, first column, what you've got? 5. If you hide this first row, first column, then you will get this one, 5, 2, 2, 2, correct? Then if you hide second row, second column, sorry, this is not the one, second column, then, so see, this is your second row and this is your second column, right? What is left? 5, 2, 2, 2, and then third row, third column. So this is your third row and this is your third column. What is left? 5, 4, 4, 5, right? Now again, you are decreasing the order. Here you've got lambda square, so here you should have lambda. So, and thereafter you have to deduct, you have to subtract the determinant of the matrix itself, which is here 5, 4, 2, 4, 5, 2, 2, 2, 2. So if you will solve this, now here it's lambda 0, lambda raised to power 0 is 1. So in this way you can easily get your values of lambda. So 5, 5, 10, 12 lambda square. Now you know we have to cross multiply. 5 times 2 is 10 minus 4. 10 minus 4 is 6 plus 5 times 2 is 10 minus 4, 6. 5 times 25 minus 16, 9 lambda minus, now the determinant of this will be, so if you do this, 5 first row, first column, what is left? 5 to the 10 minus 4, 6 minus, you have to take this one, then hide this row, this column. What is left? 4 times 2 is 8, 2 times 4 is 4, 8 minus 4 is 4, then 2. So you are hiding this row and this column. What is left? 4 to the 8 minus, so you are hiding this one, right? 4 to the 8 minus 5 to the 10, so minus 2, right? Equals 0. So you have got lambda cube minus 12 lambda square, 9, 6, 15, 6, 21 lambda minus, this is 30 minus 16 minus 4. So that means lambda cube minus 12 lambda square plus 21 lambda, 16, 4, 20, 30 minus 20, 10 minus 10. Now you have to solve this. So lambda, if we substitute 1 in place of lambda, 1 cube is 1, and this is 22 and 22, which will be 22 minus 22, 0, right? That means lambda minus 1 is one of the factor. So let's take this up. Here what is given to us is this equation, which is lambda cube minus 12 lambda square plus 21 lambda minus 10 equals 0. So lambda minus 1 is one of the factor. So how you do this? You have to solve this with this method. Okay, so lambda square, I hope you know this. I'm just telling you, if you multiply this minus lambda square minus plus, this will be cancelled out, minus 12 plus 1 minus 11 lambda square plus 21 lambda. Then you have got minus 11 lambda. So if you multiply this with this, plus 11 lambda, right? And then plus minus. So this is what we have got is here plus 21 lambda, and you are having minus 11. So this is plus 21. 21 minus 11 is 10 lambda minus 10. So you are having 10 lambda minus 10, right? So your factors are lambda minus 1, lambda square minus 11 lambda plus 10. And now again factorization, 10 times 1. So what you can have, if you do 10 and 1, which will be 11, right? Minus 10 lambda minus lambda. So factors are lambda common, minus 1 common. So lambda minus 1, lambda minus 10, and you can say lambda minus 1 square, lambda minus 10. So this is your characteristic polynomial, right? This is your characteristic polynomial, and equation is, if you put this as 0, then that will be the equation. So what are the values of lambda? From here, two values are 1, 1, and from here, one value is 10. So that means, if you see, you have got your three eigenvalues as this. Now here are two terms. One is algebraic multiplicity and another one is geometric multiplicity. Okay, so first of all, let's see what do we mean by these two. So what we have got is this as characteristic polynomial, right? So here, if you see, for lambda is equals to 1, what is the power? The order. Order is 2. So for it, algebraic multiplicity, that means algebraically how many times it is multiplied? 2 times, so 2. And for lambda 10, you have your algebraic multiplicity as 1 because its power is 1. Now in order to get geometric multiplicity, we have to find out the rank of the matrix. How do we calculate the rank? So rank is basically, you can check my other videos out also. If you see, rank is the number of non-zero rows. So you have your matrix as, basically your characteristic equation is this, right? A minus lambda is 0. So if you consider the matrix A minus lambda I, and you put lambda is equals to 1 for this, so it will be A minus I, right? So the matrix will be, your A is 5. So 5 minus 1 is 4. Here 5 minus 1 is 4. Here 2 minus 1 is 1. Rest all will remain the same. So this is your actual characteristic matrix, right? Now, in order to find out the rank of this matrix, what you need to do, remember, we are about to find out geometric multiplicity, and that's why we are doing this. So we have put the value of lambda as 1 and finding out the matrix. So in order to find out the rank, if let's see if you can reduce it into any zero form. If we do, R1 tends to R1 minus 3R3, sorry, 2R3, because if you see 4 minus 4 will be 0. So if you multiply 2 and again with R2 also 2R3, what we will get? So we will get, so this will become 4 minus 4 0, 4 minus 4 0, 2 minus 2 0. So all the elements will be 0. Similarly for this also we are applying operators. So this will become 0. Only third row will be left. That means number of non-zero rows is only 1. So rank is what? Rank of this matrix is 1. Now, in order to find out the geometric mean, what will be the value? Geometric mean, the formula for, sorry, geometric mean is here. I meant geometric multiplicity. So formula for geometric multiplicity is order of the square matrix minus what you have got in terms of your rank. So what's the order? 3 by 3. That means take any of the row or column. 3 minus rank is what? 1. So for this, your algebraic multiplicity is 2 and geometric multiplicity is also 2. Okay. So what do we mean by this? Also, if you have your algebraic multiplicity is 1, remember this is the rule that geometric multiplicity can never be greater than algebraic multiplicity. It can be equal or less than. Okay. So for this, geometric multiplicity would be 1 only, right? Now, this is your lambda 10. You have got algebraic multiplicity and geometric multiplicity for all the eigenvalues which you have got. Now it comes to convert the matrix into Jordan canonical form, and for that we need Jordan blocks. So how we will get it? See, here you have got your matrix as lambda 10, lambda as 1, right? Two matrix. So for lambda 10, your geometric multiplicity is 1. For this, geometric multiplicity is 2. For this, algebraic multiplicity which you've got is 1. Here, algebraic multiplicity is 2. Okay. So now, remember, you have got your matrix, right? Whenever you have to convert a particular matrix, you need characteristic polynomial. So basically, if we have upper triangular matrix, we need firstly diagonal elements, right? What would be the diagonal element? Diagonal element will always be for that matrix which is a diagonal matrix, we have eigenvalues as diagonal elements, right? So all the elements will be like 1, 1 and 10, right? So one eigenvalue, another eigenvalue and third eigenvalue. Three eigenvalues have been placed here in the diagonal form. Basically, this form, Jordan canonical form, we are using to convert a particular matrix into its diagonal form. So what we require is all the elements below the diagonal, what they will be 0, and above that also you will have 0, right? You will have 0, because if you see, I told you above this diagonal matrix you should have 1 always, right? I told you in the example, but that is only in the case when diagonals are same. Here diagonals are not same. We have 1, 1 and 10. So you have to place 0. You have to make it upper triangular, lower triangular, all the elements must be 0, only diagonal should be there. Now, this is the canonical form. And what would be the Jordan blocks? So Jordan blocks will be for lambda 10, because your geometrical multiplicity is 1. So only one block can be can be extracted. So what it will be? 10 of the order 1 by 1. Why we are taking order 1 by 1? Because if you see algebraic multiplicity is also 1. Then you have for lambda 1, geometrical multiplicity is 2 and algebraic multiplicity is also 2. So if geometric multiplicity is 2, you are taking it, that means you have to have at least 2 or one matrix which have the summation of order as the order of the matrix. So your order of the matrix is 3 by 3. So here what you will do, your other two elements, this is lambda is equals to 1, right? So you will take 1 and 1, two matrices of order 1 by 1, right? So two blocks. And if you see for all the Jordan blocks, the summation if you do 1 by 1 plus 1 by 1 plus 1 by 1, the order is 3 by 3. So this is how it works. If you have got this, very good, but this is a quite complex topic. So if you have any doubt, you can comment in the comment box and I can come up with some more videos. If you like this video, then don't forget to like, share and subscribe my channel. Till my next video, take care of yourself. Bye bye.